Hey, hello everyone. Good morning. Okay, let's start. Yeah, as a quick recap of what we have covered in the yesterday session. So we basically started up from big data, understanding the term and understanding its official definition given by IBM. And then we have seen the solution for the same, which is through Hadoop, and how Hadoop is basically different from other traditional distributed systems out there in two perspectives, right? One is through data locality and another one is through rack awareness. And then we have also seen about the workflow in which how the blocks are basically split, like very detailed way we have seen on different scenarios, wherein if one of your slave node goes down, what happens? And what if the master node basically goes down, and how these replication scenarios happen? Like we do face in scenarios like under replication, over replication, and how these can be tackled by the name node. And similarly, we have also seen about standby name node, which is basically the backup of a name node. And in some cases, especially if you start working for bigger clients, wherein you do have the slave nodes in terms of thousands, it is also okay to have multiple standby name nodes as a backup plan. It is not necessary that always you should have only one standby name node. I can have n number of standby name nodes too. Now, these are little advanced areas that goes when you step inside as an architect, wherein you need to understand a lot about the different scenarios that can happen day in, day out. So now let's understand further about how I can process all this, because we are seeing about good information on the basics. Now, today we'll see how all these can be practically implemented. Right now, as I said yesterday, for people who are opting for the course, like we do provide an VM, which is based on Ubuntu. And in that VM, you have all the Hadoop and its necessary eco components being pre-installed on it. So all you have to do is just download, plug in on your machine, and then you can start your VM and you can start working inside all of your Hadoop and its eco components. So let me bring in that VM for you. So this is how the VM will basically look like. It's an Ubuntu one. So if in case any of you have worked with Ubuntu before, you can find it very similar. So it's nothing but another desktop within my Windows, which is in VM. And I have plugged in through VirtualBox as a platform, Oracle VirtualBox as a platform. So now this is my VM. This is my Ubuntu desktop, and in which I have a lot of folders and files and all other applications, and in which I have installed Hadoop also. And the terminal that you could see over here, this is a place from where we are going to communicate with your storage layer. And also we are going to pass some commands so that we can extract the data, ingest the data from different sources. Okay, fine. Now, today we'll first start up with our extraction techniques, especially if I have a data. Let's first talk about very simple files, and then I'll take you into an RDBMS table, and then also I'll take you into streaming data. Now, the first type of data that we do generally handle, like 70 to 80% of the industry related projects occupied with your structured data. In that case, we do have files which are coming in the format of CSV, TSV, and all the tables which are coming in through your RDBMS, right? Could be an Oracle, Teradata, DB2, any of your RDBMS. Now, these data are basically classified as a structure, and I'll show you now how you can read them. And similarly, we do also have unstructured data, which can be again in the format of a JPEG, MP3, MP4, or text, or a DAT. I have given here only few patterns. There can be a lot more that come under the category 2. And similarly, the third one can also be XML, Avro, and JSON sometimes can be classified as structure depending upon how the data basically look like, and sometimes it can be classified as a semi-structured data too, if in case it has a lot of nested documents, nested JSONs inside. Now, let's talk about the first and the foremost simple way of ingestion, which is extracting a file which can be of any simple type like CSV, TSV, or MP3, MP4, or an Avro, Json, how all these files can be brought into your HDFS layer. Okay. Now for this, we are basically going to use some HDFS commands, which are nothing but derived from Unix. Now, if you go to my folder, you could see I have kept some files here, which are, I have a CSV, I have an Avro, I have an XML, I have a text file, and few other data type, a few other patterns as well. Now, irrespective of whatever pattern it is, if in case it's a file, then it is a common way through which you can bring it inside your Hadoop storage layer. So now let me show you how you can do that. For this, the command that you have to write, first go into the folder where you have all your files being located. Now I have this folder under which I do have all of my files. Now I am interested in bringing this particular file, let's say the sales file, the 2000 sales file.csv, right? The one that you could see here. Now I am interested in bringing this file into my HDFS layer. Now for this, the first step is I need to create a folder under my HDFS so that it will be easy for me to push this file inside that folder. So how I'm going to build a folder? Very simple, like how we build a folder in your Unix using the mkdir command. The same way you have to use it over Hadoop also. Just that if you observe in all of your HDFS commands, it is very simple to write HDFS commands, provided you know or you have some basic understanding on Unix. You don't need to write complex shell scripts kind of. If you know the very basics like how to copy a file, how to create a file, how to bring the first few lines, or how to cut a file. So if you know such basics on your Unix command, then that can be directly converted into your Hadoop command. Now, how that can be done? Simple. Write Hadoop fs hyphen, and then you have to write all your Unix-based commands. 1 second. Yes. Now, what these Unix commands, what are the list of Unix commands that come under this category? So now you can have an starting from a very simple ls, right, which helps you to list out the commands, cp, which helps you to copy, mv, right, which helps to move, and cat, which helps me to view the content of the file, head, which can help me to view the top few lines of the file. See, I'm just going by all this with an assumption that you have some idea on the Unix command. If not, you have to touch upon some basics on Unix so that things will become much easier. Fine. Now I'm going to build a new directory under the folder. So now I have a folder called home Hadoop under the root directory, of course. So I call this as Learnbay, something like this. Now what will happen? There is a new directory which gets created under your Hadoop file system, because this mkdir command is prefixed with your Hadoop fs, which basically tells you it's not on your local file system, it is on your Hadoop based file system. Now see, I'm going to do an ls on the same folder so that I can confirm whether it has been created or not. Okay, no more notification to me saying that it does not exist. So the directory is basically been created and it holds good. Now let me push this file, which is there on my local file system under the Learnbay webinar folder, into my Hadoop folder like this. Now how you can do? Hadoop fs hyphen put. Very simple. Put is a command which helps me to bring all kind of files inside my HDFS layer. Okay, so bring the file which is there on your LFS and then push it inside this HDFS folder, source destination, right? So have the file here, push them inside. Okay, now it has been done. Now how I can cross check again? Do a very simple ls, right? So that you should be able to see that this file has been pushed inside my newly created directory under my HDFS folder. The same way, see now, right now I have I moved a CSV file. The same way you can move all kind of file. Now I have a very simple Avro-based file. Now I'm interested in pushing the same command. Okay, so when it is a file, the process is so simple. Just use the simple command called put and you can push it, provided the file is residing in some location and the file is as whole, so that you can directly bring it into whatever HDFS layer you want. Just specify the explicit path, the full path, so that the file will be pushed into that particular. See, now we have pushed 2 files inside. The same way I can push whatever file that I want, irrespective of the format, irrespective of the extension it is, I can bring it. The only thing it has to satisfy is it should be a file. Okay. You can't move a folder like this. It should be of a file. So this is a very simple ingestion technique wherein I have a file and I am pushing the file inside my HDFS storage layer. And remember one point, the moment when you push a file into your HDFS layer, automatically at the back end, all the process that we have learned yesterday happens. For example, like I'm right now bringing the Avro file. Imagine the file is of some 256 MB. Now, the moment I write a put command and specify a HDFS folder, for us, all these stuffs are not visible. But then at the back, this file will be pushed inside your HDFS layer and it gets divided into whatever number of blocks right here, and they will be stored in different slave machines under your cluster. Though you don't get a view of all this happening at the back, we do only get a view like, okay, the file has been pushed, but at the back, internally, all the processing, the block conversions and replications and getting stored inside different slave machine, all of them happen at the back. Okay, now I have my HDFS layer. Let's imagine this layer is my HDFS. So now if it comes, if I need a file to be brought into this particular layer, I know just now we have did, you can use the Hadoop put command, which basically helps me to, okay, fine. But now what if my client is saying, now, no, I don't have a file, rather I have some huge bunch of tables which are sitting under a DB called Oracle. Okay, or a MySQL or a Teradata, whatever it is. Now, and your client is interested in bringing them into your Hadoop layer, then you can't do it in this way, right? Because this is only specifically applied for your files. Now, how about tables? How about RDBMS content? Now, that is where we are in need of a new component called Scoop. Now, only through this interface, I can bring any kind of file, sorry, any kind of data which is stored in a format of a table in RDBMS into my Hadoop layer. I'll show you how to write this. There are some set of commands which you need to follow, quite simple ones. If you write and if you execute them, then it will try to establish a connection between your RDBMS and your Hadoop layer. And through the connection, it will extract whatever table that you are interested in bringing. Okay. So yeah, so till this place is it clear? Any questions so far? I'll show you now about the scoop. So before I want to show you in the lab, I just want to check if there are any questions. Okay. And if in case anything is there, please report it over the chat. Fine. Now, this is for an RDBMS, right? Now, how about if your clients are saying that they are getting files from a web server, okay, or from a log file, which will periodically get increased. For example, like I'm getting a streaming data like this. Now, initially it comes at a speed of, let's say, 10 Mbps, and then slowly it comes to 50, 80, 100, and so on. Now, how about reading such kind of data which comes to me in real case, in the sense like the data keeps on coming to me at a speed and I have to read them. Now, in that case, again, scoop cannot help you, and even the put command cannot help you. That is where we need to understand another ingestion technique called Apache Flow. And both Apache Scoop and Flume are coming from Apache Software Foundation itself, and hence they are absolutely open source. You can go to scoop.apache or flume.apache.org and you can download the tarball for it. Now, how Flume works simply? Again, we need to write some configuration file for Flume. Now, what my Flume will basically do, it will try to establish a connection with my source, and my source can be any web server from where I'm getting streaming data, and those data can be pushed into my storage layer of Hadoop, which is basically my HDFS. Now the interface here is basically your Apache Flow. Okay, let's see both of them, because bringing a file in its batch form, it's so simple. Just by writing an Unix command, you can do it. But then when you want to practice through Scoop and Flume, in case of reading the content from an RDBMS or from streaming data, it's a little bit different process. So let me show you. And by the way, these two components are pre-installed on your VM, so you can directly use them. So you don't have to download anything for that. Okay, now in your VM, because if you want to practice your scoop, then we need an RDBMS in place, right? So that I can establish a connection with my RDBMS and I can extract the data into my Hadoop layer. Now, and for that reason, I definitely need an RDBMS in place. So in your Ubuntu, we have MySQL being pre-installed. So this is my MySQL, which has been installed locally on this VM. So inside this, you can go ahead and build some tables and databases. And those tables, if you want, you can practice by extracting them into your HDFS layer. It does not provide any DB drivers for it, but then we have to establish a connection by the component called scoop. Now, it does not have a predefined list of DB drivers that it has, but then you can connect it with whatever RDBMS that you want by providing this interface called scoop. So to scoop, you have to provide this driver, and scoop has all these drivers been installed on it. Because as such, Hadoop is not only meant for reading RDBMS, right? So scoop is what if we say scoop is a placeholder. The scoop is trying to fill it, the place between your RDBMS and Hadoop. So when you download in Hadoop, you will not get any DB drivers by default. Now, when you download Scoop and when you are establishing an interface, that is where you will get all this. Fine. So if you see here, I have in MySQL table here. Sorry, I have in MySQL been installed here. Now, these are my credentials. It is a local one, so it is perfectly fine. Now, I can have a lot of tables inside, and I can have a lot of databases inside for my practice. Now, I have a DB called training. Okay, and inside this, I have a table called comments. Okay, so I'm going to show you how you can take this table on this local system, the table's content, how I'm going to bring it into my Hadoop layer. Now, not necessarily always your RDBMS has to be locally available on your cluster, right? Cannot be the case. Think logically. See, you're a company who is working in India and who is working for a client who is somewhere over US or Australia. Now the thing is, they are saying that they have their database located in a centralized space in some other country, and we have to connect, you have to establish a connection with the RDBMS from that geographical location, and we have to extract the data, push it inside our Hadoop cluster for some of the processing. So now in that case, your RDBMS is not locally available to you. It is somewhere available in the cloud or somewhere available in your client server. All we are doing is establishing a connection from my cluster to the corresponding distributed system and then extracting the records. So it can be in both ways. It can be locally available also, or it can be extracted from some other server or distributed system in place. Now, how in industry-related projects we generally do is, of course, at the final production implementation, you will be basically reading it from your client's DB. But then when you are initially building it, you will have a local DB in your pseudo-distributed system. You will mock up some data similar to the data that you are going to work in your production, and you will keep it locally, and then you will start building your exercises, your projects. So that's how. Keeping them locally also helps, and keeping them in real time in wherever your client's location is there. Your RDBMS could be any place. From there also we can read it. Now for you right now, being in a webinar, I show you this in a local mode, wherein I have my MySQL available locally inside my VM, and all I'm interested is going to extract this whole bunch of comments table into my HDFS layer. Okay, now for that, we need to write some set of scoop commands. I won't call it as a programming as such, but it contains some list of keywords and parameters which we need to pass as comments, and that gets executed to bring the data inside. So now quickly, I will walk you through the architecture behind your scoop. The reason is, any real case project you go, definitely like 70, I mean, I would say not 70, 80 and above of the projects will definitely have the data coming in from any of your RDBMS in place. And if you are having your Hadoop in place and if you want to process them, you need this component compulsory. Okay, irrespective of the RDBMS that you are trying to connect. Now, how this is going to work? So Scoop has a framework. Now, what this framework will basically expect, the location of your RDBMS. It could be either locally available, as I said, or it could be somewhere outside in a cluster. Now, whatever it's a location, specify the location detail first. And then under this RDBMS, what is the DB from where I'm interested in fetching a table? Now, in our case, if you could see, there is a DB called training, right? Under the DB training, we have a table called comments. Now I'm going to extract that comments table. Then specify the table that you are interested in extraction. Now, after you specify these three details, it will also ask you for a few other details, like what is, if in case it's been credential protected, your RDBMS, then you have to provide the credentials also. And along with that, the most important information that we have to provide. So I will write credentials first. Now, along with this, you have to provide one very important detail, which is how many splits you want to convert this table so that it can be read parallelly and it can be pushed inside your HDFS folder. See, this is very important because in all of your RDBMS table, if you can see in a real case scenario, the records will be really huge, right? Tables will be having records in terms of lakhs, hundreds, thousands, right? And reading them sequentially is not going to help me by any means. So definitely I need to think of a plan on how I can parallelly read this huge bunch of records on my table. And by default, Scoop splits the table into 4. Now, why 4? 4 is just the default number, like how we have the replication factor as 3 for your Hadoop. So 4 is a default split number for your Scoop, which means Suppose I have a table which contains 100 records inside it, then it is basically from 1 to 25, it will store in one block. I mean, it will store in one split. From 26 to 50, similarly from 51 to 75, similarly from 75 to 100. So basically 4 split of records it will take, and all these 4 splits will be parallelly read and it will be pushed inside one single HDFS directory. Now within the directory, I will basically have 4 files. Now why 4 files? Because we have 4 splits. Now, is there any possibility wherein I can change this number? Very well, you can change it. Now, suppose I feel like, no, the records in my table is even higher, somewhere in terms of 20 lakh or 30 lakh, and it is splitting them into 4. I'm not getting the best out of parallelism. Is there any way I can increase the splits? Very well, you can increase the split. You have to pass the number as a parameter, and based on whatever number you are passing, it will split the table into that many splits, and all of them will be parallelly read, because it's just a reading, right? It doesn't need any dependency. Correct? We are just going to read them. So you can read them parallelly and you can write them inside a single HDFS directory as either 4 files or 10 files, depending upon how many splits we have done. Okay, is that clear? Okay, let me show you how these commands you can write. As you know, we are going to have this table called comments. Let me just show you first some sample records from this table. So this is how my table looks like. It has some 5 fields, and I think it has somewhere around some 60,000 records inside. And this is a pattern of the data that it holds. Okay, wherein the ID field is basically your PK, and it has 4 more fields on it. Well, now let's try to bring this comments file under our HDFS folder called Learnbay_web. We just now created a folder, right? So I'm interested in bringing into a folder like that. So let's write some scoop commands. So if you want to see how the scoop command structure will basically look like, okay, let me show you this first and then I can write it. See, this is how the scoop command will basically look like. So now in real case situation, we can also automate the scoop jobs. Now, how to build basically a scoop job is, so the commands are scoop job. These are the keywords. And we do have all these bunch of parameters. Now there are a lot more other parameters which go in a little advanced phase in the next phase. But then if you want to read a table from an RDBMS and through a job, then these are the essential and the basic parameters that you need to supply. Okay, first, what is a parameter is -- create, specify a name for your scoop job. Now, why we want to create it as a job? So that whenever we need, we can re-execute it. You don't have to write all of these parameters again and again. You can simply write an execute command, specify the job name so that it gets executed. Okay. For re-execution of a particular set of commands, you can use this scoop job name. And then -- import. This is just a parameter because extraction from an RDBMS to your HDFS is basically called scoop import. Similarly, we can also do the reverse, vice versa, which is from your HDFS into your RDBMS is also possible. If you want to do that, then it is called scoop export. So both can be done. So in your real case projects, now initially you will bring the table from your RDBMS into HDFS because RDBMS cannot handle such a huge load. Just as a storage, it is fine. But then when I start writing complex queries, it is getting hanged up. And for that reason, I'm bringing them into my Hadoop cluster. I do all the processing here. I got the output, and the final result, if I'm interested in again pushing it back into my RDBMS, you can do that through a scoop export command. Okay. And the third parameter is connect. Now, what a connect is, this is a most important parameter, which is basically telling you through which credentials and through which port number and host name, basically you want the connection to be established. And all of us know the whole of Hadoop is built in Java. So obviously we need a JDBC connection to establish connection with an RDBMS. And what is the RDBMS to which I need a connection to be established? Now it could be as I said, could be an MySQL, or it could be a Teradata, or it could be any of your other RDBMS where your clients are keeping the data. So specify that. And then specify the host name and the port number of your RDBMS. Okay. Now, why we need to specify this? Then only I can establish a connection with that particular RDBMS through which the records can be read. Now, since I have my MySQL locally installed on my VM, I'm calling it as a localhost. Now, suppose imagine your clients are saying, no, it is available in some other location, and this is the URL of that URL you have to use in order to extract it, and specify it over there. And the port number on which your RDBMS is basically installed. For every RDBMS, there is a particular port number. In case of MySQL, it is 3306. Similarly, for TD, for Oracle, it changes. And the last one is basically your DB. Now, after you establish a connection with your RDBMS, from which DB you are interested in reading the data. So you have to specify the DB. And then your credentials, because most of the time you will protect your RDBMS with some credentials, and hence you need to specify them if you want to establish a connection. So specify those details and specify the table under this DB which I'm interested in reading, and specify the target location, right? Which is basically your HDFS. And the last and the most important parameter is -m. This is nothing but referring your number of splits. Now, as I told you, by default, it's going to be 4, right? When I establish a connection and I'm trying to read it, it is always going to be 4. Now, if you feel, no, I don't need 4, I need a number of splits to be either less than 4 or it has to be greater than 4, then accordingly you have to pass this parameter called -m, because this is going to decide on how many number of splits you want to basically create. Okay. Let me show you how we can do this. So first step is just simply write the initial keyword, which is scoop, and then your top. You can write them in next line if you feel like writing them in a single line seems to be quite big, or if it's not in a readable format, most welcome. You can write them in multi-lines also. Just that as a carriage written, you have to give a slash. And then I'm writing create. Suppose I'm writing Learnbay. You can write it any name, by the way. And -- import -- connect. Now connect is the place where I will basically provide my details. This is a port number and this is a DB from where I'm interested in reading. And what is the table that I'm interested in reading? As we know, the name of the table is comments, and the username for my MySQL is root. And generally in real case situations, you don't give, you don't hard code the password. But then if you are working on a single system, it is just between you. I mean, it is just for you, then you can very well hard code the password directly by typing _password and then a password. Or else you can give it like -caps p. The caps p will not expect you to give the password hard coded here. Rather, when the job is running, it will extract it from you, and which will be in an invisible mode, so that we are taking the security into account, right? And finally, your target directory. Your target directory is basically your HDFS directory. So I'm just trying to give the same name. Oh. Okay, I pressed mistakenly control. Let me come. So I will write like Learnbay web demo. You can write any such names. Does that make sure whatever name that you write, that's going to be created under your HDFS bucket. Now, I'm not specifying the -m parameter that you could see here in this, because here we are changing the 4 into 1, which means sequentially I'm trying to read. Now, I don't want the read to be happen sequentially, and hence I want to go by the default number of splits, which is okay. Now we start executing it. Now the scoop job has to be created. Ask for the password, give the password, and then the job will be created. Now, once you created the job, all you have to do is execute it. We know the name of the job, right? This is the name of your scoop job. So simply write -exec and then the name of the job. So now this will start executing your scoop job, which will internally establish connection with your RDBMS, start extracting the records, push it inside this folder as 4 splits. Okay, let's wait for a second so that the job will be done and we can see the record. Can you have a read here? It is basically the number of splits is going to be 4. Nowhere I have mentioned it, but then it's going to take it as a number of splits to 4 because by default it is. And based on what column it will actually split. Now, I'll show you the meantime it runs. I'll show you here. See, now you could see there is a PK here, right? ID is a PK for your table. Now, based on the values of your ID, it will try to split them into 4 parts. See, otherwise what happens, there can be duplicates in your table and it will not make the splits to be equal, right? For that reason, whenever the split is happening, it will always look out for a PK on your table, and based on the values of your PK, it will try to split the records on your table into 4 parts, so that I can say very well that the split will be at its best in terms of equal number of records. If not completely divisible by 4, of course, there will be few records here and there extra, but then definitely one of the split will not be overlooked if in case I start splitting them by using my PK. Right now, the whole of the scoop job is done. And as you could see, it has retrieved some 50,000 records inside. The total number of records in the table is somewhere around 50K. So it has retrieved all of those 50K. Now, how I can see this, right? What it is saying is it has extracted the table into my HDFS folder. But then how I can see it, go to your directory and do a simple ls. Now, when you do an ls, you will basically able to see 4 files which are coming up over here with different naming conventions. right? Now the naming convention basically starts from part -m, and it starts all the way from 5 zeros, and then it gets incremented starting from its ones place. And then what will happen after it becomes like this? It will start incrementing from its tens place, 1 0 1 1 like this, and it goes all the way up to 1 9. Then it will become 2 0 like this. It goes all the way up to 9 9. Now, the reason why I'm saying all this is because it is capable to produce that many number of output files for you. Now, if you want to have huge number of blocks, because the table is really bigger, then very well you can go to a maximum. Just imagine how many number of files you can create. If the file naming convention starts from 5 zeros all the way up to 5 nines, right? So it gives you this wide range of files that we can generate by specifying the number of splits on our tables. Now, let me also show you how the content look like, because that is more important, right? Because there it was in the source, it was a table, right? Now it has become a file. So we are interested in seeing how the record will then look like. If you do a cat on this, it's not recommended to directly do a cat on it because the files are really bigger in size, but I'm just showing you because I have very little amount of records with me for the sake of a webinar. But then if you have good number of records, you can use the head command. So when you use the head command, you can limit on how many number of records you can see. Right? Fine. Now see the content. Go to the top. Now, if you could see, there are records which are coming in this pattern. Now, how I can cross-check whether this is how my table also look like. See, this is my table, right? Have a look on them in both the places. Okay, so this is how the data over here looks like. This is how the data over here looks like. Now, if you could see, the data is similar. Of course, it's not the exact data because this is a part file. This is a starting. I did a limit file. So the top 5 records alone you could see. But then if you see the pattern, you can easily make out the records from the table is only been pushed inside your file. With one difference, if you could see here is, whenever a column has been done, here the delimiter over here is automatically coming as a comma. Correct? In all of your rows, you could see the separator for your column, because it's basically coming from a table. So I need to have a character which basically separates the columns inside it. And that is where by default, it goes with a comma in it. So by this way, I can basically bring in any kind of records which is there inside my RDBMS table. It could be of any column, any number of records. I can bring them into my HDFS file. Okay. Is that clear? If you want me to show one more time the scoop command, let me show this. Can have a look on it. Let me know if you have any questions on it. If you're not able to understand any of the parameter, or if you have any doubts on any of the parameter. Okay, I believe you're doing good. Now, in the same command, okay, you can do a lot of changes. Like, for example, it's not always necessary that you have to completely read the whole of your table from your RDBMS. As I said, I have a comments table which has some 50K records in it. Not always I need to extract the whole bunch of records in it. I can add an other parameter called query here. query. Now what the query parameter will do, write any query, which can be a combination of multiple tables also. It can be a union of multiple tables, or it could be a join of multiple tables. Now the result of the query alone will be fetched into your HDFS. Right? So how cool is that? So it's not necessary that always you need to extract the whole of the table and then process. While extraction itself, you can limit the number of columns or the number of records by using another parameter called query, which is of very, very useful in many situations. And this is one parameter. Now, similarly, I can also use another parameter called columns. Okay, wherein I have to read all the rows, but not all the columns. I can set a limit on the number of columns, specify the name of the columns, so only those columns will basically be extracted and pushed inside your HDFS layer. And similarly, we can write fields terminated by. See, all these parameters we'll discuss really in deep with an exercise in the class, because it takes quite good amount of time, so which can't be completely covered in this 2-hour webinar, but all these parameters will be taken. Now, fields terminated by is another parameter. Now, what this parameter will do is, by default, you could say comma is a separator, right? Now, suppose there is a downstream project which expects the record from your RDBMS, but they want in a different pattern, wherein they want the fields to be separated by a hyphen or a slash or some other character other than comma. Then you can specify this so that when it extracts and it pushes inside your HDFS layer, it changes comma into whatever you are specifying. Okay, and similarly, when you are doing multiple rounds of execution, for example, so today I'm running a job wherein my table is having some 100 records. So when I do an import, I extracted all those 100 records. Now tomorrow, my client is inserting on the same table 50 extra records they are inserting. Okay, understand very carefully. So it's not like in a new table, on the same table, along with that 100 records, I'm inserting 50 new records freshly today. Now, when you do an import, then I will basically extract all the 150 one more time. Of course, I can limit them by writing the query parameter, but then if not, it will extract again the 150, wherein the 100 becomes duplicate, correct? Now, in that case, we again have an incremental append feature. Now, using that incremental parameter, we can specify till what record has been imported before, so that you have to read only the latest records, which is the newly inserted records into the table, into my HDFS. Got it? And similarly, I can specify this -m parameter, through which I can control how many number of splits I want. Now, basically, when the number of records in your table is really lesser, wherein I'm not interested in splitting them and using them, rather I can do a simple sequential read itself there, then you can use the -m parameter as one. So if not, anything greater than 4 also we get. Okay. Fine, guys, any questions? Okay. Now, let's move on. So, yeah, got some. Now, let's move on into the next set of extraction, or the next set of ingestion technique, which is basically your Flume. Now, what do you mean by Flume over here? Flume is basically another extraction technique through which I can read the data which comes to me at a streaming speed, right? Initially itself, I explained when when we have started seeing about the two extraction type itself, I told you. Now, Flume is another eco component And what is it being useful for? It is basically used to extract the data which comes to us at a specific speed. Now, if you see this picture, you can clearly understand. Now, I have some streaming data coming in from an external source. Now, this external source can be from a web server, or it can be from servers of different kind like Netcat, or it could be an XML file which has been basically getting loaded by using a shell script. Now, it could be of any pattern, any type data. But then the only requirement, it has to be a streaming data, which comes to me at a particular speed. Now, what is this Flume component is going to do in order to extract this streaming amount of information is, it expects you to write a configuration file, which is very simple because it's not something that you are building from scratch. So there is a template for this configuration file. All you need to do is you have to pass parameters saying what is your source name, what is the HDFS location where I'm interested in putting all the streaming data. So these parameters which are exclusively applicable for you, you will specify inside your configuration file. And based on that, the records will be extracted and sourced inside your HDFS layer. And Flume can also integrate with other file system apart from HDFS2. Now, for example, if I want to upload into AWS, okay, or if I want to upload into GCP or any other cluster, not necessarily it has to be in HDFS. So, but all these details we have to specify on the configuration file. So accordingly, it will source the data. Now, other than the source and sink, right? So this is basically your source and this is your sink. We need to configure one more element, which is basically called the channel. Now, this channel is nothing but a pathway through which the records which we have extracted from your external source will be pushed, and that will basically go and reside under the destination storage layer. Now, this is a very higher level view of how a Flume configuration happens. So simply extract it from a third-party source, pass it into a channel, and then place them into a sink layer, which is basically can be an HDFS or any other storage file layer. Now, but internally, how the operation happens is it's a little bit lengthier process. Now, for example, let's take, I'm reading this data at so-and-so speed. Okay. Now, this data comes to me. It cannot be directly written into the HDFS layer for a simple reason. The number of, the time and the data that you can read at a particular speed cannot be written parallelly, right? There will be definitely a lag in between. Right? For example, if I'm downloading a data at a particular speed, I cannot upload it on that same speed. Definitely there are differences when you start uploading it. Now, that's a very simple takeover. So I'm reading the data at a speed, say 80 Mbps, but then when I'm writing it, I can only write it, let's say, at a speed of around 40 Mbps. Then a bunch of 40 MB data on the first second need a placeholder to be stored, right? That is where your channel comes in picture. So now this whole 80 MB of data will transfer through this channel, and from that 40 MB will first be pushed inside your HDFS, and then in the next second, like that, it keeps on read and it keeps on pushes them inside your HDFS layer. Till how much records you are reading it, we have to write them also, but then the speed will vary. The speed of reading and the speed of writing will certainly vary because it cannot be the same. And the difference amount of records, the delta records, will basically be stored inside your channel. And from the channel, it will be transmitted at a particular speed into your sink layer. Okay, let me show you a configuration file. See, this is a template. Again, you don't have to get panic on saying, do I need to write these many lines of code? No, it is just a template. Okay. All you need to do is you have to change the values at runtime for what are all your source and your sink. Now, when I initially start my Flume configuration file, if I want to configure it with so and so source name, then specify that. Now, second time I want to configure it with some other source, then change only the source. Similarly, if the second time I want to change the sink alone, then only change that particular value. So basically, you don't have to write these many lines of code for every single time when you want to extract it from Flume. Got it? Let me walk you through the configuration file. It's very, very simple. So the whole of your code basically gets divided into 5 parts. The whole of the configuration file, if you break them down and see, it is very simple. So it's basically going to contain 5 parts, 3, 4, and 5. Now, the first part is a place wherein I'm going to define or I'm going to initialize my source, my channel, and my sink component. Now, how I can define it? The first word, if you could see in all these lines, all the names are constant, right? It is called Flume_tab. Now, what is this refers to? So this is called agent. Now, every Flume will have a source, will have a channel, and will have a sink, right? Now, together, all these 3 can be represented or can be called as a one single Flume agent. And this is going to be the name of that agent. So whenever I call it as a Flume agent, it is nothing but a consolidation of your source, channel, and sink. Now that's why, if you could see the name, all of the line, it starts with that because all these components belong to that one single agent. Now, Flume_A1 is the name of your agent. And in that, what is the name of your source? What is the name of your sink? And similarly, what is the name of your channel? And see, again, here there are a lot of advanced areas too. So I just will cover only one part. Now, if you could see the names, you might find that all of them are coming in plurals, right? Sources, sinks, channels. So now these are the parameters. So it is fixed. Now, why it has been mentioned like in a plural form is a single Flume agent can read the data from multiple sources. That's why. Now, these 2 sources can be sent into one channel. From there, it can be drained again into multiple sinks. These are little advanced areas. You don't have to go so detailed into it, but just understand that this is also possible. And similarly, I can also have multiple like this channels, and both these channels can drain into one single sink also. That is also possible. So you can have n number of sources in one single Flume agent, n number of sinks, n number of channels, depending upon how your use case and business depends. So that's why if you could see the names, they are all in terms of plural. Okay. Fine. Now, first line, simple. I'm going to provide a name for my source. In my case, I'm just going to have one single source. So I'm calling my sources source 1. Right? See the name. Similarly, I have a channel and I'm having the name of my channel as C. And I have a sink wherein the name of my sink is going to be sink 1. So now how the records are going to be pushed in this pattern. Right? By seeing the first 3 lines, you can imagine the picture and the names. How does it look like? Now, the second bunch of lines will basically explain you about the details of your source. So I need to mention from where I will basically read the data. Right? It can be a web server or it can be a netcat, could be any kind of servers. So specify the details of them. So for an example, I'm going to show you a netcat. So I'm writing the netcat. and it is inside my single machine itself running on this particular port. So the source configuration is done, and then come to the sync configuration. Now you can write it in any order also, not a problem. You can write the source component, then the channel component, then the sync configuration, or you can write it in whatever order you want. So these three can switch over their places too. Fine. Now here again we are going to describe about my sync, whether it is going to be a HDFS layer, or it's going to be connected to an AWS, wherever it is, wherever your file storage is going to be. And then the location inside that layer, and then in what format. So format is default being assigned to text and data stream, as we are reading a streaming amount of data. And similarly configure the channel. Now the channel, the type will basically be of two. One is called mem channel, another one is called the file channel. Now both can be used. There are few configuration differences between them. So now the main difference is, if I go ahead with a file channel, even if at some point of time, if my agent stops, the records which were there inside your channel at that particular point can be retrieved back. If it is memory, it cannot be retrieved back. So that's the difference. So the type you can specify, which can be either of mem or file. The whole capacity in terms of bytes, okay, and the transaction capacity again in terms of bytes. So this is a very small number that I specified to show you with an example, but in industry situation, you can have it in a higher number, but it has to be a number in terms of bytes always. Okay, and finally, the configuration part, or sorry, the binding part of your source, channel, and sync, which is basically establishing this line. So which tells you this source has to be connected to this particular channel, and similarly this sync has to be connected to this particular channel. So establishing this line is what? The last part of your code, which is basically your binding. Got it? So now if you write these 5 different steps of values and you start running your configuration file, and also parallelly start your source, because if your source is not producing data, the whole of your Flume configuration is of no use, right? The source should produce the data, and then you start your Flume program, then you can extract, you can understand how this extraction basically works. Okay. Now, running this Flume program is a very, very simple process. I'll mention you the command for it. It is going to be Flume -ng, because initially when they have this component in Apache, they call it as Fluming. Then later it has been changed to Flume. So that's why the keyword that you used for execution still remains the same, which is Flume -ng. And then an agent is a keyword. It refers to the name of the agent with -n as a parameter, and then specify the name of your agent. And then the next parameter is -f, wherein you have to specify the name of your configuration file. Done. Okay. Now, when you do this, after you start running, what it will basically do, it will start all your source, channel, and sync. And once it has started, then you have to start sending the records from your source. And once you start sending the records through the channel, it will be absorbed, and then it will be stored inside your sync layer. Looks logically bigger than simple HDFS because I'm trying to, yeah, correct. Exactly. But the point is, you're not going to build it every single time, right? So not a big deal, right? So it's just that change the values accordingly for all your operations, though it looks logically bigger. Right, now let's come to execution part. So I'm going to show you a simple sample of how you can run a Flume code by reading it from some source. And the source also, I can start it manually inside my VM. Okay, let me show you where my file is. Okay, I have the same file being stored here. Okay, for saving some time, I have the same file being stored inside this particular file on this folder under a name called netcat flume. Now I'm going to run this. So let's first get inside the folder. This is the folder in which we have our configuration file. So let's go by the syntax that I mentioned. So flume -ng, right? And then agent -n, specify the name of your agent. So now go inside your file and check what is the name of your agent so that you can type it, and -f, name of your file. That's it. So, you know, once you start running it, it will basically start opening up all your source component, your channel component, and your sync component. Now you could see it has been started all your channel, your sync. See, the name of our channel is C1, right? And the name of our sync is sync1, the name of our source is source1. It has been established. All this connection has been established, and it is waiting basically for the data to read from my source port. So I'm going to start and port on the number that I have specified inside my file. And here I can start writing some data. I'm just taking some sample data. You can also type it over here. Okay. Now see, I'm just feeding some values. Let me take something from the log itself and feed. Now you don't need to do this manual feeding in industry situation, or even I will show you in a WebLogic case on a real class, where in that time also you don't have to do it. So it will automatically get populated with the records inside. See, now I start feeding some data from this particular port number. Okay, I'll feed few more. I'm just copying content from here and pushing it. If in case you're wondering what is happening, it is just I'm not interested in typing them. So I'm just taking some sample record from there and pasting it from this particular port number as a streaming data. Okay, now the data has been streamed. It can keep on getting streamed. Now come back to this particular place where your Flume program is executing. Can you see some new lines been coming up? Previously, we were only till this place wherein all the connections have only been established. Now, if you could see, it starts coming up. Now, what these lines represents, if you understand this, it's very simple about the Flume process. See, initially it creates a file. What is this folder? This is nothing but the folder that I have mentioned as my HDFS file. And inside this, it creates a file with an extension called TM, temporary, right? And the name of the file is something like flumedata.timestamp. Let me stop the source or else it will keep on being waiting for the records. Yeah, I'll come back here and stop this. Yeah, now if you could see, now it initially created a file, right? Now what is this number? This is just an epoch number of your timestamp. And then it will start pushing the records inside it. See, it started at 45 and then around 54, which is exactly around some 9 or 10 seconds. Now what it is basically doing is it is closing that file, the file that gets created at this time, by changing the extension from .tmp into without .tmp, which is basically it changes a temporary file into its original one. What this simply means, see, now when we are reading the streaming data, it can come at any huge speed, right? starting from somewhere in kbps all the way up to mbps it can come. Now, how much amount of record I have to keep inside a single file, I need to tell to my flow. So within a particular second, how much ever of data comes to you, you can store them in one single file. You can configure that number. Like the default is going to be 30 seconds or 10 seconds, which means for a period of 10 seconds, how much data comes to you, push them inside one single HDFS file. Similarly, the next 10 seconds, read whatever data comes in, pushes inside your HDFS. Similarly, the third 10 seconds. Like that, for a particular fixed duration, you can write, and based on that, the records will be stored inside a file. Now I have closed my source and the job as well. So let's see how the file looks like under this path. Okay. Let me take this file. So I'm just taking one random file just to see what is the content inside the file. I'm just doing an ls to check whether I'm in the correct one. Okay, I'm inside that only, so I can do a simple ls. Okay, it is small. So go to your Hadoop fs ls and put a slash in front and it's a slash. And now you could see this file is there. Okay, now let's see the content inside by writing a cat command. The files will be really lesser, so I'm doing a cat command instead of a head. Okay. If you feel the records will be more, you can use the -head command. Okay, so can you see that these are some of the records? I'll show you in my source screen too. See, these are the records that we have initially pushed, right? See, from my host name. Now, those are the records, can you see here on the first file? Right? But of course, you might observe something wherein it comes as an SEQ file, which is basically in its sequential form, compressed form. The thing is, obviously the data comes in that particular duration will be really bigger. I don't want to store it in its raw format under my HDFS file. That's why by default, Flume itself will convert it into its compressed form as a seq file, and it stores inside whatever directory we need under your HDFS. Got it? Clear? Now I'll show you a few more files also here, because we have got, I think, 2-3 files as per the notification of your program, right? So this is one timestamp, this is another 3. After that, I actually closed my source, so that's why you're not able to see anything. Now, the first file I showed you, let me show you the second file too. Now again, if you could see the data that I have pushed in from my source, right? That is only getting extracted here on my HDFS level. Now, depending upon the default time frequency, now the records have been read and they are stored inside your HDFS file. If you feel like, no, I can read even more number of records in a file. So maybe I can change the frequency time from 10 seconds to, let's say, 60 seconds or 120 seconds. Very well, you can change that. So now how you can do that is you have to go and write an extra parameter for your Flume configuration file. Say roll count, hdfs.roll count, and then you can specify the seconds, the time in terms of seconds, so that for that particular second duration, it will keep on reading the data. and store it in one single file. And after the duration is done, it will open the second file, third file, and so on. Okay, that's clear on Flume. Perfect. Now, let's move on to a very, very important topic, which is your Mapreduce framework. Many of you would have known this before, or if not, maybe you would have heard it somewhere. Mapreduce framework, which is one of the most prominent framework, which paves the way for today's computation in terms of big data. Though it is not being much used now because of some of its disadvantages, which are being overtaken by the new computation framework called Spark. But still, this paves the way for all sorts of computations which are existing right now with respect to big data. So let me explain you how this Mapreduce framework basically works, or what is Mapreduce data. So it is nothing but the computation framework. Like how we have a storage layer, HDFS is basically your storage layer. The same way, Mapreduce is nothing but your computation layer or a computation framework. Now, processing is a little different compared to the way that we are storing it. Though process happens parallelly, but then consolidation happens only when all the different blocks are getting processed, and then any one of the slave machine which has enough memory and CPU capacity can come and consolidate all the intermediate output and generate your final output. And this can be basically taken care by a resource manager, which is a master service, and node manager, which is the slave service. Now, I'll show you how this map framework basically works, because I just thought of showing you with an example so things can be easy to understand. But then before that, earlier, the Mapreduce framework can only be built through Java as a programming language. Right now, we do have a lot of alternatives. Forget about Pig and Hive. We can write a Mapreduce program in Python. You can write it in Scala, Ruby, and all this other programming languages. Now, other than this, Apache as an organization, they have come forward with these two new components if you want to deploy Mapreduce. Because in the earlier days, when it was initially pitched in, Java is the only language through which Mapreduce can be achieved. Now, we are in need of highly qualified Java professionals in order to build a Mapreduce. So that was one of a challenge. And hence these two components came in, wherein Hive is one of the components through which I can write some queries. And the queries, I do call them as HQL, okay, Hive query language. Now using that, I can do my Mapreduce. So same way, Apache Pig is another component, wherein I will write my program through a language called Pig Latin. And then that's also quite simple, easy programming language to work with. But then the challenge in Pig Latin is it has a lot of limitations. When it comes to flexibility, it's not that flexible enough in processing wide variety of data. And that's one of the reasons it's not quite popular. But Hive can handle it really well by writing queries. Fine. Now let's comment it, because we are not going to do it with Java or Pig or Hive right now. Hive, of course, I will show you because most of you will have some SQL knowledge. So we can see how to build Hive tables and work with. But before that, I'll just give you an idea on how this framework will basically work. Okay, so they have disabled whiteboard. Okay, fine, no problem. This is the best place, it's not whiteboard. Quickly check it out. Fine. Now let's see this. Let's take a file like this. I mean, just trying to show you with an example for your MR approach, like how the processing basically happens. Let me take this. Yeah. So imagine this is your HDFS file. Okay. Now, when you are having an HDFS file, obviously it gets divided into certain number of blocks, right? So I'm just dividing this till this place. I'm calling this as block 1, block 2. Of course, it will be much bigger, but for us to understand it, how the parallelism work, I'm just logically considering these 3 are the different blocks which are stored inside my HDFS layer. This is one single file, which in turn gets divided into 3 blocks. Now, all I'm interested in doing, the processing that I'm interested in doing is, I'm interested in finding out the average temperature, okay, recorded in every city. Now the file is really bigger. Let's imagine the file is somewhere around some 600, 700 MB. Okay, so it's certainly bigger, and it has repetitive cities coming in inside in every individual block. So overall, I'm interested in identifying what is the average temperature recorded in every city. So if I start working sequentially, certainly it's going to take a lot of time for me to do it. And that's why I'm coming into Hadoop, so that I can make all of my slave modes to be ineffective, and I can achieve it really quicker by using my distributed approach. Fine. Now the whole of the Mapreduce framework, let me put it somewhere here. Now the whole of your Mapreduce framework is basically divided into 2 main phases. One is called map phase and another one is called reduce phase. So what this phase will do, what will happen inside this phase, all of them, let's see. Now, in between these 2 phases, actually there is one more phase, which is called a shuffle and sort, which generally we don't talk a lot about it because it's going to do the same job irrespective of whatever data that we do. You'll understand it when we come to it, okay? Now, I'm going to prepare a program to identify the average temperature recorded in every city on this huge file. Now, and I'm going to give it to the master. So what the master will actually do, the master will create multiple copies of the same program. And the first copy of the program will be sent into this machine where it stores the first block. And I call it as M1, which is basically mapper 1, mapper 2, mapper 3. Now, how will this mapper basically work? It can read the data only in the format of key value pair. Now, what do we mean by key value? Simple, like if in case you guys have studied or if you have used Python by any chance, you know the dictionary over there. So from there, you can understand what's a key and a value. So there will be a key and associated value along with that. Now, every record inside every block will be read by the mapper. Now, when it reads, it will not read as it in original form. Rather, it converts it into a key and a value pair. Now, what a key means? Key is nothing but an offset. Value is basically your entire record. Now, what do you mean by offset? For example, I'll take this first line because it is in the first block, and mapper M1, which is basically the program, is applied on this. So it takes 0 and this whole line, for example, 1930, 15, when MNS. This is your value and 0 is your offset, which is your key. Now for the second record, again it will write 1940, 29, min, SF. Like this, for every row inside your first block, the M1 will read the file and convert it into a key value pair like this, wherein key is basically your offset and value is the entire record. Now your M1 also prepares this, your M2 also prepares this, your M3 also prepares this. Okay, I'm just writing only one sample so you can understand how it works. 39 min SF. Like this for all those. Similarly here also, it's going to be 0, 1975 and all this. Now what happens is, this is an input. Now after it reads this key value pair, your mapper program or the program that I have basically written for finding the average temperature, I will write a logic such that in order to identify use case, what are all the fields I will. See, I don't need the year, by the way. I don't need the level. All I need is a temperature and a city. Now within these two, I need to identify what will be the key and value with respect to my use case. So what I'll do, I will convert this record, right, the first record, into a key value pair like MNS, which is my city, and 50. Now this is going to be my key and a value. Similarly, the second record, I don't need the score with respect to this use case. All I need is, from this row, I need only the city, which is SFO, and the temperature. Similarly, this whole row I don't need. Though I need it, when I read it, I have to read it in that way. But then after I read it, based on my use case, I have to convert my input into an output pattern. So I'm converting SFO into 13. Similarly, this one also, I will convert it like MNS 78. Now like this, for every row inside every block, your mapper will basically generate an output. Now that is called map phase, the initial phase, wherein it reads the records in an offset and the entire record and converts it into the key value pair based on our use case. Now, once your mapper phase is done, wherein basically you are converting the file in its necessary key value pattern, because the whole of Mapreduce framework can only work in a key value pattern, and hence every phase you have to convert the data into a key value. Now it needs to be shuffled and sort in the second phase. Now, as I said, it's a generic phase. You don't have to write any logic for this. But then how this shuffle and sort phase work? It will take the output of all of your mappers and it will look like this. It will shuffle them. So let's take in MNS. From the first block itself, I have two temperatures coming. See, 34 and 15. So it will take 15 and 34. Similarly, from the second block, I have 78. Any other MNS? Okay, nothing. Now, similarly, from the third one, is there any MNS? Yeah, there is one more 78, right? And one more 78 too. Now, like this, it will shuffle the value of a similar key. Now, whenever there is a key is coming in from all the different mappers, the corresponding values will be shuffled and will take us in single list of values. Now, this is for MNS. The same way I'll do it for SFO or whatever different locations we have. Like, for example, something like JHK and ERF and so. Now, lot of data transfer happens only in the shuffle and sort phase, wherein whenever a key is matched, all its corresponding values will be taken and it will be kept. So, which basically stands for the first F, which is your shuffle phase. Now, after your shuffling is done, it will sort them based on your keys. So, sorting will happen only based on your key. Of course, if the keys are it's a string, then it's going to happen based on the alphabetical order. If not based on, if it's a number or a floating point value, accordingly, it will be sorted in the ascending. So that's going to be your shuffle and sort. See, there is no logic for your shuffle and sort, right? Like for every individual use case, the logic will not differ. You can find an average temperature here, or you can find the maximum sales that has happened on a particular month. Whatever logic that you're writing, shuffling is going to be taking the same key, combining the values, and then sorting them. So there is no extra rule or logic that I need to write for every use case. In all your program, it goes and follows the same workaround. Then comes your reduce phase. Then what is your reduce phase is going to do? It will take this key value pair MNS, and then from this whole bunch of iterables, it will apply the logic for my use case. So in this case, it's a simple average. So it will do an average, add all of them, right? Sum them up, divide it by my count so that I will get an average. So I'm just taking some random average here. It could be somewhere around 40. Okay, somewhere I'm writing it as 40. Now the same applies for all of your keys, JHK, and how actually this will happen in your cluster. Any one of the slave machine will actually read the shuffle and sort output, apply the logic on this list of values, and generate your final output. So let me take this to be something like 39, 40, and 32. Okay, pardon my handwriting, it's not so good, but I hope it could be kind of readable. Yeah, so that's how all these three phases basically happen. So it's a map phase which initially happens, then it goes to shuffle and sort, and then finally it goes into a reduce phase, wherein you get the output for your use case. Okay. Yeah, any questions? Yeah, Aishwarya. Okay, anybody else is having any questions? Perfect. Okay, if you guys are clear on this, then this is your very, so it was a use case with the static data. See, at the end, the dynamic data will basically be taken from your Flume and it will be stored in a batch file, and the batch file will be given into a MR. Now, when it comes to MR, it can handle data only when it is in its static form, in its batch form. If you want to read streaming data and also parallelly want to process it, I think that's what you mean, right? Then, like reading them dynamically, and also if you are interested in parallelly processing them, then MR cannot support in that case, because MR cannot work on real cases, real streaming data. That is where your Spark computation framework comes in. Inside Spark, we have a component called Spark Streaming, wherein it can read the data dynamically and it can also process them in real time. Right? That is one of the disadvantage of MR also, I would say, because for a good number of period, this itself was a huge thing in solving big data problems. So when it is in a batch file, processing them and solving them itself is a big deal. And hence MR was there in the industry for a quite good number of time. But then once all this around like last 7-8 years, wherein streaming data is becoming the next big thing, MR is not doing its best, because MR cannot handle streaming data. If you give me a batch data, it can do its job very well, but then streaming data it cannot support. So that's where the new computation framework called Apache Spark comes in, wherein one of its components can do the same job really well. Fine. Guys understood this MR, then the last thing that we need to understand is how about implementing this MR? Of course, implementing MR in Java is the initial way like even when I initially started explaining all these concepts to my students, I do explain them in Java, but then slowly the usage of Java has been kind of, not much people will be aware on all the nuances of Java. So we do need an alternative, especially something which is with respect to SQL, because that's one of the common knowledge many people in the industry have. That is where Apache Hive comes in picture. So now Apache Hive is again an open source component. You can download it from hive.apache.org website. The good news when it comes to Hive is you don't have to write any complex Java codes for achieving this use case. The example that I have just now shared, right? The average temperature. Now, in order to implement that in Java, you basically need to write 3 classes. So one class is for your mapper, wherein you will write a Java code by reading them, converting that offset and a value into your key value pair. And then you will write another class for your reducer, wherein you will write a logic of reading the list, calculating the average. And you will write a third Java class, which is basically a driver program to call all the above 2 class. So the simple logic itself will easily take around some 30-40 lines of code when it comes to Java. But then when it comes to Hive, all I can do is convert this file into a table, and then I can simply write an average of temperature group by city. Job is done, correct? Of course, it can't be applicable for all scenarios, but in certain scenarios, the job can be done really easy, especially if you want to write and process them in the query. And the good thing is, all you have to do is write that simple query, like average of temperature, group by city. Now, internally at the backend, all your statements that you're writing will be converted into mappers, shuffle and sort, and reduce ways, and you get the output. So you don't have to worry about, okay, how I can convert this into key value pair, or how this query will be run at the backend, because at the front end, you will write an Hive query. Internally, the query gets converted into an MR job, and the result will be fetched out to you. Okay, and another simple thing or easy, I would say, when it comes to Hive is it deals with tables, right? So let me show you how to log in inside that. So simply type Hive. Again, Hive has been installed on this VM, and that's why you can directly access it. If you want to manually try them out, then you have to download Apache Hive separately, and then you have to install it inside your VM, and you have to start. Okay, let's have a quick read over here, and then I'll show you. So Hive is consistently used in the analytics section of your Hadoop, as it provides an SQL-like interface. And since SQL knowledge was common, it's been used by a lot of people. And Hive is an Hadoop-based data warehousing tool, which supports a language called either HiveQL or HQL. And all sorts of queries that you can basically write on your MySQL or on Teradata or on Oracle, you can very well do it in Hive also. There are few limitations, but that is applicable only when you start writing subqueries in Hive. Otherwise, in general, it can be used in the same syntax that you use on your MySQL. Now, here, I'll show you quickly on how you can build a DB. The same commands that you use in other RDBMS. So I'm writing something like Learnbay Data. This is a DB that we are building. And then getting inside the DB. Okay. Now, if suppose I'm interested in converting a file into a table and processing it, okay, now this is a CSV file that I have. Okay, now all I'm interested in doing is converting the CSV file into an Hive table so that I can perform some processing on top of it. So how to create a table? Same way that you do in your RDBMS. Create table if not exists, Olympic, and then check on the data. So I'm calling this as a name. Each country, yeah. Date played, I'm calling it as a string. And sport also, I'm calling it as a string. Gold, silver, bronze, and then, okay, total. So these are the list of column names that I'm interested in reading them, and I'm loading it from a file. So obviously we need to do the row format delimiter fields terminated by your delimiter. And of course, if you observe, it comes up with a header on it, right? So I need to handle my header. Table properties, skip header line. How many number of lines I basically want to skip. Okay, fine. The table has been created. Now you can load it. So I'm specifying the location from where I can take the file. So name of the file. Okay. Input table Olympic, right? So I will write a function through which you can see the column name. This is just a property. Okay, fine. Now I'm going to see whether the table has been done. Okay, the table has been loaded, and I also want to see some samples. Okay, now if you can see, the CSV file has been basically converted into a table on its structure, and you can do all sorts of queries. Like as I said, you can find the average, or you can do a ranking. For example, like suppose I'm interested in ranking the people based on the category of sport that they have played and based on the total number of medals that they have obtained. And I also, after categorizing them, I'm interested in fetching the top few ranks. So then in that case, I can do a dense rank function, right? And I can apply partition by category and then do an order by your total and then arrange them in the descending fashion, and you can do it. So similarly, you can do, sorry. Similarly, you can do all sorts of, yeah, similarly, you can do all sorts of your group buys, your order buys, and then different joins on your different Hive tables. So the queries I'm not going to in greater extent because any RDBMS query that you write, you can very well put it over here as well, and you can extract the results. So this is how you can build a simple Hive table, and you can convert a file into a Hive table. Now, I have shown you here within CSV file conversion. Now, the same way, we can also load a JSON file and an XML file also. They are little bit advanced in a way, wherein because XML files cannot be directly loaded like the way that we have loaded in CSV. So we need to use a function inside Hive called XPath. So using the XPath, we can specify the tag. For example, see, I'll show you this file. So now this is some random XML file that we have taken, because sometimes in your industry situations, you are expected to work in XML files too. But then processing the XML file is really a hard thing, because Writing them in Java needs lot of steps wherein you have to split them based on the tags. You have to read the tags, store it in a location in an iterable one, and then read them. And based on the iterable, you have to split it. Now, rather than that, you can also convert this XML file into a very simple Hive table by using an Hive's inbuilt function called XPath. Now, using the XPath, you can specify the tag name. Now, that tag name will get stored inside a column on your Hive table. So we'll see on how to load an XML file into a Hive table in our regular classes, and also we'll see on how to convert a JSON file into a Hive table and a TSV file as well. But then remember the fact, all these can only be done if your data is in its structured format. I mean, of course, apart from your XML, provided in XML, we are manually doing certain changes so that it can be easily converted into a structured content. But then if it is a simple text file, which does not have any pattern running on it, then I have to go ahead with your a pig, or I have to go ahead by running a Java code, or even in Spark also you can handle it. Hive's table cannot do the job for us in that case, because it always expects data to be in its structured format. Got it? Clear on how you can enter inside Hive and you can start building the table and you can query the table? Any questions with respect to Hive? Now, overall, it basically gets divided into two types of tables. One is called internal tables, and another one is called external tables. Now, internal tables are also referred to be managed tables, wherein these tables are basically getting created inside your Hive, and it's specifically used only within Hive. Now, when you build external tables, they can be used from other eco components too, need not necessarily be used only inside Hive. It can be accessible from Spark, or it can be accessible from your pig or from other components too. Now, how you can basically build them is, when you are building a table, right? When you're writing a create table statement, when you're writing a create table statement, if you simply write create table name, it's all going to be your internal table or managed table. But then when you're building it, if you write a keyword, say external table and then a table name, it is all going to be your external table. And when I build an external table, it can be accessible from other components too. But that's not the case in your internal table. So that point you need to understand when it comes to the different types. Other than that, creating it, loading it, and writing queries on it, it is absolutely same. The only difference is the accessibility of it. Internal table, the scope is only within Hive. External tables, it can be accessible from other components. The full use case of the full use case of work with big data via Hadoop, etc., is a preparation phase for exactly then. So how it basically happens is, see, I'm doing all this prep up work and I make the life of a data scientist or a machine learning expert simple. So I do all the basic stuffs for you. I give the data and it's completely consumable format so that a data scientist can come and take it. He gets the data and it's in its completely usable form, and they can build models out of it, and they can do whatever forecast they are interested into it. So your understanding is exactly right here. So it mostly comes as a prep phase for your data scientists. And also in terms of analytics. So if I think since you are from the background of data analytics, you're asking this. So yes, so you can also take it into data analytics field as well. If you delete external data, see, that's again a huge area, Nani. So external table, if you delete it, the records within your Hive will not be accessible because it's an external table, right? You cannot permanently delete it. When I build a table and if it's an external, within, and if I'm trying to delete it from my Hive's window, of course, within Hive's window, it's not accessible. But then when you're doing it from Spark, it is still accessible because it is an external table, not only specifically limited into your Hive. Okay, we'll see in very detail about how to build this external and internal and few other points to take care of it because it's a huge area. So all these areas will definitely be taken in the actual classes. We'll build some tables and we'll see how the differences in MR happens. And if you delete it, what happens, and all those logic will cover there. Yeah. Fine, guys. Any other questions? That's it from my side here for this second day. So we have covered about the Hive, the scoop, the Flume, and the Mapreduce approach on how it's going to be used. We'll discuss a lot about each of these areas in detail with a lot of use cases and exercises over the class. Considering the time of 4 hours will not be enough for doing all this webinar. Yeah. Fine then. So that's it from my side. If you have any questions, yes, please do put it over the chat. And Ishan, are you there?
Yes, ma'am.
Yeah, you can take it forward from here. I'm done from my side.
Sure, ma'am. Thank you so much for this webinar.
Yeah, you're most welcome.